Welcome to the next video in our System Devices 2 networking series. Again, we're going to go down that protocol stack. This time we're going down to layer 2, our data link layer. Okay, so what have we looked at so far? So in the last lecture, we looked at our layer 3 protocol, our internet protocol IP, and we saw how those IP addresses could be used to route our packets across our network, across the network of networks that is the internet. However, those logical addresses, those IP addresses, are not actually what we use to identify our hosts on our local area network, our LAN. This raises the question, why not? Why don't we just use IP addresses for everything? Why do we need another way of identifying our hosts on our network? Well, let me take you back to lecture 1. So in lecture 1, to illustrate the concepts involved in packet switch network, we use that mail delivery analogy. So we want to post a letter from our house to another destination, somebody else's house. So on that letter, we write the name and address of the person we want to send it to. So we can consider that to be the IP address, the thing that identifies the host on that bigger network. Now, the key thing to identify here is that the address is used to route the packet from one point to another, but how it is carried between those points will vary. So in this case here, it's carried in the mail bag, it's carried in a van, it's carried in a plane, carried in a train. So if your letter was travelling across the country via train, we're interested in the railway station. We're interested in specifying how that train gets from one railway station to another railway station. So the information that we're using to move our letter from one point in the country to another point in the country is not the address on the letter. That decision's already been made in the sorting office. What we're using is the name of the stations. So a completely different way of identifying where that letter is going, where that packet is going. So we're decoupling the address that is on the envelope from the transport method. Equally, you can think of it from a different point of view. Think of it in terms of the computing hardware we're using. So if an IP address was burnt into each computer, yes, we could use that to identify the computer. And let's say we're using that computer as our web server. So it would be identified on our network using that IP address. But eventually all hardware wears out and that computer needs to be replaced. And obviously the new computer will have a new IP address, which will obviously have an effect on our DNS system. And obviously that would need to be updated with that new IP address. However, if we have that separation in that the IP address is a logical address, and each machine on our local network will be identified by a physical address, a MAC address, an Ethernet address, then we've got that separation. We can keep the same IP address for the computer, and the communication across that local network will be performed using that physical address, that MAC address. And changing that won't affect any of the routing that is involved in our layer 3 networking. So communication at layer 2, at our link layer, will be different to that used in layer 3. So down in layer 2, we could use any protocol to carry our layer 3 IP packets. It doesn't matter. But typically, you will see it's the Ethernet protocol, because over time that has evolved into the industry standard. So Ethernet protocols use MAC addresses to identify the hosts on this local area network. And that's what we're going to be investigating in this lecture. Righto then, so we're moving down to layer 2, the link layer. So our unit of data transfer at this level is called a frame. And in general, these are the things that switches deal with. So at this layer, we're looking at Ethernet protocol and we're looking at MAC addresses. And as I said, that is the language your switches will speak. However, in addition to that, we do need some translation between layer 3 and layer 2. So layer 3 talks IP addresses and layer 2 talks MAC addresses. So we need some way of resolving one to the other. So we need some way of converting our IP addresses into MAC addresses. So as always, we need a protocol for that, and that's ARP, the Address Resolution Protocol. And again, we'll be looking at that in this lecture. So our Ethernet protocol is not defined in an RFC, it's defined in a standard because it's maintained by the IEEE, which I find makes it harder to find in some respects. It's far easier to Google an RFC than it is an IEEE standard document. As you can see here, there's some different flavours. So Ethernet is the 802 standard, and you can see over time different things have come and go. So our token ring networks, which were still about when I first started, but now have been superseded by obviously our Ethernet protocol. So we do have 802.1, you'll see that in VLAN specs. Main one would be 802.3 and 802.11. So 802.3 are your copper hardwired standards, and 802.11 are your wireless standards. As you probably guessed, over time these have evolved, and that's when we start to add letters to these names. So if we looked at our 802.3 standard, we started off with our 10base2, our coax cable, Ethernet standards, and over time they've evolved. And the ones in the lab, we're using 802.3U, and that is a 100 megabit standard, bidirectional fast Ethernet. Obviously, Raspberry Pis will do faster than that, they will do gigabit, but the switches and the routers we have in our base systems are only 100 megabits to save a bit of money, to be honest, because our system, we're not really looking at any high performance considerations. So our Ethernet protocol, created in the 80s, as I say, IEEE standard 802.3, and it is the default protocol you'll see on your local area networks. So hosts, as we were saying, are identified on these networks using MAC addresses, or to give them their full name, the Media Access Control address, and these are 48-bit addresses. So each network interface controller, each NIC at manufacture, is given an unique 48-bit address, is given a unique physical address that will identify it on our network. And typically when you run ipconfig or ifconfig, you will see that represented as 6 two-digit hexadecimal values, as you can see in this example here. So just the same as our IP packet, when we put our Ethernet frame onto the network, it will have a source address and a destination address. So in your IP packet, you had a source IP and a destination IP, and in your Ethernet frame, you'll have a source MAC and a destination MAC. The next bit in our header is the Ethernet type, so an identifying number that identifies what is contained within the payload, what type of data this frame is carrying. So if you saw the Ethernet type 800, you'd know it's an IP packet. And that payload will typically be 46 to 1500 bytes long. Then finally, at the end of our bit stream, we will have a checksum, a cyclic redundancy code, a checksum that we can use to test for any errors, single event upsets, bit flips that may have occurred during this packet's transmission. There are some variations on the theme that you might see out there, so if you were to use the 802.1Q format, then you would see there's an extra field put in between the source MAC address and the Ethernet type fields. So that standard allows you to define virtual LANs or VLANs. Effectively, it's a way of subnetting your layer 2 Ethernet frames. It allows you to assign each host onto a specific virtual network, a VLAN. So only hosts on the same VLAN can communicate with each other. So hosts on different VLANs will be completely separated from each other. They won't be able to communicate with each other unless they went through a router. So effectively, it's a way of partitioning bigger switches into separate, smaller virtual switches. So rather than buying 2 separate physical switches, you can do exactly the same using VLANs in one big switch. And that offers you a lot of flexibility of where physically these machines are in the building. Normally, if you're connecting to your local switch, then you'll be in the same geographical kind of area within the building. All the machines would be close together, connected to that same switch. However, now we can have the machines in any part of the building and just logically connect them together using VLANs, which gives you a lot more flexibility in your wiring. So rather than having to run specific cables to connect machines in different parts of the building to the same physical switch, you can all just do it logically using VLANs. However, as you probably guessed, your switches have to support VLANs, and there's some small issues connecting multiple switches together. There's always a cost, nothing is free. Okay, a question. Why do we define a max and min size for this frame? Why don't we allow an Ethernet frame of just 1 data byte? Why does it have to have a minimum of 46 bytes? So even if you just wanted to transmit 1 byte, you'd have to pad it out with an extra 45 bytes to get up to its minimum length. Equally, why do we define a maximum length as well? And you probably guessed we will chat through those answers in the lecture review session. So here we have our Ethernet header. Well, I suppose it depends what you count as a header, really. I guess more accurately, here we have a diagram of our Ethernet protocol stuff. So we have 7 bytes of preamble. So to synchronize the transmitting and receiving machines, the transmitting machine will send out a sequence of 1s and 0s to allow the receiving machine to determine what clock rate the transmitting machine is transmitting at. Then we have a start frame delimiter to signal that the data is coming. Then we have a 6-byte destination MAC address, a 6-byte source MAC address, a 2-byte type field, and a 4-byte frame checksum. And then obviously we have our payload data, which will typically be our IP packet. So in total, if you include everything, that's 26 bytes. But I guess strictly speaking, you could say, well, the actual header that has the information is 14, but I'd also chuck on that checksum at the end. We do obviously with UDP and TCP, so in total that would be 18 bytes worth of query finger time header, because obviously the checksum comes at the end rather than the beginning. Okay, so our MAC addresses, those 48-bit values that identify our hosts, are constructed from two parts. So we've got 24 bits worth of organizational identifier and 24 bits of network interface identifier. So our organizational unique identifier are the first 6 hexadecimal values. So if you look in our test systems, the 192 network uses those USB to Ethernet adapters. So you'll see they all start with the same organizational identifier because they're all made by the same company. And again, the other network interface, the NIC that is actually on the Raspberry Pi PCB, they would typically all have the same organizational identifier, but they do vary now. Obviously, Raspberry Pis have been around a while, so there's more than one flavour of network controller now. So if you are interested to find out who your MAC address is registered to, there's a website for that. So if we were to take one of our MAC addresses you can see in this diagram and we enter it into this web page, so macaddress.io, it will tell you who it's registered to. So surprise, surprise, MAC address is with the organisation ID B827EB, were the original Raspberry Pi Foundation MAC addresses. And again, we can do the same with our current Raspberry Pis. So if you go to the VNC session and you do an ifconfig, you can see the various network interfaces. So if we take the MAC address for the onboard NIC, we shall see it is again registered to Raspberry Pi, but now it's Raspberry Pi Trading Limited. There we go. The lower 6 hexadecimal digits are your interface controller identifier, and these values will be burnt into the actual hardware at manufacture. So I'm guessing there's some OTP memory in there, so one-time programmable memory. So when your network controller, your Raspberry Pi chip is being tested, they can program this MAC address into that memory, burn into that memory, such that it can't be altered, a value from their pool of allocated MAC addresses. Okay then, so our switch in many respects looks exactly the same as a router, but internally obviously they're fundamentally different. A switch does not understand IP addresses. It knows nothing about IP addresses at all. Well, I suppose unless it's a layer 3 switch, but we'll gloss over that one for the moment. In the lab, the switches we have, so these ones here that you see are dumb switches, so they know nothing about IP addresses. All they know about is MAC addresses. So on your switch you will have a series of ports, and a port is something you plug a cable into. Yeah, I know we have some reuse of terminology here. So obviously in TCP we have the concept of a port, and when we use our TCP and UDP API we have the concept of a socket, a thing you connect to the network through. So I'm doomed. So what do you describe that as without reusing the terminology? In networking, we call them ports. So these are ports, but equally calling them sockets, obviously that clashes with our TCP and UDP. They're holes in the switch. So the holes in the switch where you plug the cables in, at layer 2, we call ports. And they are given a number. So they are identified within the switch as either port 1, 2, 3, 4, or 5 in this case here. And a key thing that a switch does do, it can learn what is connected to what port by analysing and keeping a record of what source MAC addresses it sees coming into these ports, thereby detecting what host is connected onto the other end of its various cables. So, okay then, question. If our application code knows about IP addresses, because when you wrote that UDP program or the TCP programs in the labs, you specified your hosts using IP addresses, you didn't specify them using MAC addresses, how does your host identify what MAC address it should use? Because on layer 2, we do not use IP addresses, we use MAC addresses. So we need to convert our IP addresses that we do use in our network layer into the MAC addresses that we use in our data link layer at layer 2. So, as always, we have a protocol for that, and that's the Address Resolution Protocol. So our ARP protocol is a layer 2 protocol, so it doesn't use our transport or network protocols such as UDP, TCP and IP. It works in the layer 2 level, so it can only be transported across our local area network. And as you probably guessed, if we're trying to find out who has a particular IP address, we need to send a packet to everybody, so we need a broadcast address. And that's what the all ones MAC address is. So MAC address FFFFFFFFFF is our broadcast address in layer 2. So as always, our payload is organised as a bucket of stuff. So our ARP packet will have this generic payload that it uses to hold our requests and our replies when we're performing our translations from IP addresses into MAC addresses. So we have some various fields here. So from memory, don't quote me on these, but we've got a hardware type. You can perform ARP requests on different types of networking hardware. So I think type 1 is Ethernet. Then we have protocol type. So what protocol you're performing your ARP request for. So IP is 800 hexadecimal. Well, that's IP version 4 is 800 hexadecimal, and IP version 6, 86DD hexadecimal. But do look those ones up. Then you got your hardware address length. So for MAC addresses, that'll be 6 because they're 6 bytes long. They're 48 bits. And we have our protocol address length. So for IP version 4, that will be 32 bits or 4 bytes. Operation, you can specify you're requesting an ARP resolution, an ARP conversion, or this could be a reply. And if it's off your reply, then it'll have the actual data you're looking for contained within this bucket of stuff. We then have fields. So we've got our sender's MAC address, our sender's IP address, our target MAC address, and our target IP address. So this container is pushed out onto the network, it's broadcast onto the network, and hopefully there's a host on the network that can fill in the missing blanks and answer your questions. So to see this protocol in action, let's look at an example. So in this scenario, we have 4 hosts. We've got the PC, we've got Pi 1, Pi 2, and Pi 3, and they are connected on the same local area network via a switch. Each host is connected to a particular port on that switch. So PC is connected to port 1, Pi 1 is connected to port 2, Pi 2 is connected to 3, and Pi 3 is connected to port 4. And that is important because that relates to the switch's source address table or SAT table. This is how the switch learns who's connected to which port, because that is the key difference between a switch and a hub. So a switch will learn who is communicating through which port, identified by its number, and then it can use that information to direct packets it received to that particular machine. So in this example here, if it receives an Ethernet frame, it will look at the MAC address, the destination MAC address, and if it matches one of these entries, it knows which port it should forward that data to. So if it receives a packet with the destination MAC address 6C2408BB981E, it knows that it should put that packet out of port 1. And that's the advantage of a switch. If this was a hub, if it receives a packet, it will retransmit that packet onto all other ports, except the one it received it on. So it effectively does a broadcast. So that still works, but it does mean that other machines are receiving packets that are not for them, which they will have to process, wasting time. Equally, from a security point of view, it's not good to broadcast all your data. You would like to keep that just private to you. So equally, if Pi 3 is transmitting stuff to the PC, you can see it will communicate across this path here. But obviously, now that we are not rebroadcasting like a hub would, this link between Pi 1 and Pi 2 is free as well. So that could be operating at the same time. And that is the advantage of a switch. Okay then, so in this scenario here, we've got an example of the SAT table, and you can see from here that previously the PC and Pi 3 have communicated because their MAC addresses are in this table. So the switch learns by looking at the source MAC address in each Ethernet frame. So as a host transmits data to the switch, obviously the source MAC address will be the MAC address of that machine. So that's what the switch records. So that's how it learns what is connected to each of these various ports. Okay then, so previously the PC and Pi 3 have communicated with each other. So they're both transmitted packets onto the network. So the PC transmitted a packet to Pi 3, for example. So the switch learnt the MAC address for port 1. Then Pi 3 transmitted a packet back to the PC. So the switch recorded for port 4 the MAC address of Pi 3. However, before the PC could initiate that communication, it had to discover the mapping between the destination IP address and its MAC address. So the PC, as we saw with our Python programs, will know about the IP address of Pi 3, but it has to discover the MAC address for Pi 3, because at this layer, layer 2, it's talking MAC addresses. So before it can communicate to Pi 3, it has to use the ARP protocol. It has to discover the MAC address for Pi 3. So it will send out those ARP requests. It will receive back from Pi3 its MAC address, and it will log that in its ARP table. And that's what we can see here. So by running the command ARP-N, we can see what previous communications have occurred on our PC, because there's an entry mapping the IP address of Pi3 to its MAC address. And it will have discovered that through the ARP protocol. So to see that in action, we can consider the scenario, okay, what will happen if the PC now wants to communicate with Pi2? So again, the first thing it will do is it'll look at its ARP table. It says, do I know the mapping between Pi2's IP address and the MAC address that I need for my Ethernet frame? So again, it will know the IP address of Pi2, so it'll know that it wants to communicate to 192.168.101.2 in this example here. So it'll look for that IP address in its ARP table. So right, it's not there, so therefore it will have to do an ARP request. It'll have to send packets out onto the network to say who has the MAC address for that IP address. So the PC will use the ARP protocol, so it doesn't know where that should go, so it makes that a broadcast. So you can see the destination here will be all ones. It'll be the FFFFF MAC address. Obviously the source address is where it's coming from. So it'll send that to the switch. The first thing the switch will then do is look at that source MAC address and says, is this in my SAT table? Do I know who is communicating with me? And in this particular case it does, because the PC has previously communicated to Pi3. The switch will then look at the destination MAC address. And again, if that was present in its SAT table, it would then know to forward that packet to that particular port rather than broadcasting it to all ports. So in the event it doesn't know the destination MAC address, or if it is the broadcast MAC address, the switch will broadcast the packet to all the other ports. So it will forward that packet out of every other port except the incoming port, obviously. So because this is a broadcast, all the different Pis will receive and process this packet. And basically it will look and go, right, does the IP address as specified in the ARP header, so this address here, the target protocol address, does this IP address that is in this 32-bit header here match my IP address? And if it does, it will respond back with its MAC address. So obviously in this scenario here, we have 192.168.101.2, which matches Pi2's IP address. So the Pi1 and Pi3 will just drop that packet. It's not for them. But Pi2 will respond back with a reply packet. Obviously it will update the destination MAC address with the MAC address of the PC, and it will set the source MAC address to its MAC address. So the first thing the switch will do, obviously it will receive that packet, it will buffer that packet, and it will look at the source MAC address and it'll go, right, is this in my SAT table? And it'll go, no, it's not. So I haven't seen this source MAC address before, so it'll add it to its lookup table here. It will also look at the destination MAC address and it goes, right, have I seen this before? Yes, I have. So because there's a match, it will send this packet out on port 1 to the PC. It won't send it to obviously to Pi1 or Pi3 because there's no point. So it has learned where that destination is by observing the source MAC addresses. So now the PC can add that relationship, so that mapping from IP address to MAC address to its ARP table, and now it can use that to transmit that Ethernet frame out onto the network. So now it can complete that Ethernet frame with the destination MAC address for Pi2 and put that packet onto the network and send that datagram onto Pi2. So we can see that in action, and I think we do this one in the lab as well. So what we can do is we can remove an IP address from a host ARP table by using the -d. So ARP-d IP address will delete that entry, that mapping from its lookup table. So if we were then to ping that same IP address, you would trigger an ARP request. So it would send out that ARP packet onto the network asking who has the MAC address for the IP address that I am looking for. Okay, quiz time. So we're going to look at that basic ARP scenario. So that ARP request and reply interaction, but now for multiple switches. So you can see here I've added an additional switch to our normal setup. So we have our 3 Raspberry Pis, our router, our switch, so switch A, and now I've added switch B. So we're going to look at how those ARP requests operate over multiple switches. So what would happen if I was to do this? So now we have the 2 switches. So Pi 1 is plugged into our first switch, and then I have a patch cable, that's a short Ethernet cable, to the second switch, and then Pi 2 and Pi 3 are now plugged into this switch. So if you looked at the network diagram, it would be like this. So here are two switches. This is our original switch, this is our second switch. So now, will this network still work? Are these hosts on the same broadcast domain? When we place our ARP packet onto the network, will all these machines receive that ARP request? Will they respond to those ARP packets? And how will they respond? In particular, what about this connection here? So remember that a switch learns what is connected to what port on the switch by examining the source MAC addresses of the packets coming in on that port. So port 1 and 2, nice and simple. So the PC will send a packet to that switch. So all source addresses on this port will come from the PC, because the only thing connected to that port is the PC. Same for port 2. The only thing that will be sending data to the switch will be Pi 1. But for this one here, Pi 2 and Pi 3 are connected to switch B, which is then connected to our second switch. So you can imagine here, traffic from Pi 2 will come in on switch A through port 3. Traffic from Pi 3 will come in to switch A through port 3. So you've got two source addresses. So what will happen inside the switch? How will that be recorded in the SAT table? Okay, another scenario to consider. So again, exactly the same setup. So switch A and switch B. So Pi 1 and the PC are connected to switch A, and switch B has Pi 2 and Pi 3. But now, just because I don't like to see empty ports, I have put another patch cable into these two ports. So will that still be okay? So from a network diagram point of view, I have put in a link between ports 4 and 5 in that one here. Will that cause any problems? Will our system still work? Not to give the game away, the answer is no. No, you'll get a broadcast storm here and the whole lot will stop working. But can you see why it will stop working? Again, think about what will happen when an ARP request goes out there. What will happen when the PC makes an ARP request? What will happen when it sends out a broadcast MAC address? Can you see why bad things will happen? Again, another scenario. So this one here. So rather than having one cable to the second switch, from switch A to switch B, obviously two cables will be better, allowing you to send twice as much traffic. What can go wrong? So again, in the network diagram, we have this scenario. So you have one connection from switch A to switch B, and another connection from switch A to switch B. And remember, these are cheap switches. So these are switches that do not support link aggregation or trunking or spanning tree protocols. So can you see any problems there, again, from a broadcast point of view? Finally, what if we mix up our switches and our routers? So Ethernet 0 on the Pis, the onboard NIC, is normally connected to the MikroTik down the bottom here. But what if we connect those to the second switch, switch B, and then connect this switch via a patch cable to switch A? Would this still work? Would these network interfaces still be able to communicate data between themselves? Now, the answer to this one is no, it won't work, but maybe not for the reasons you're thinking about. So again, the routing table for each Pi will be as shown here. So this is the routing table for Pi 2. So can you see what changes you could make to this routing table to allow these network interfaces to operate? So fundamentally they can work, but if you make some changes to this routing table, and again, if you do that, you will be able to communicate between those network interfaces. Okay, so the answers to all of these questions, as you probably have already guessed, will be discussed in the lecture review session. But do ever think about it. Do ever think about those connections. So what do I mean by that? So think about what will happen in these different networks when you go through the same process we discussed in this example. So when I send out an ARP packet onto that network, it will send out to broadcast, which causes a switch to retransmit those on all the other connections, except for the one it received it upon. So if you take that knowledge and apply it to each of these network scenarios, what will happen? What will happen to those broadcasts? And for some networks, it'll be perfectly fine. And not to give the game away, for some networks, bad things will happen. And can you see why? Step through it. But as I say, we will be looking at those in the lecture review session. Okay then, a pause to consider moment. So we're looking at our IP protocol, and we've seen it in action when we use it with our ping command, for example. So here we're pinging a IP address. And normally, if it's working perfectly fine, we'll get a response packet back from the host we're pinging, and that will tell us the RTT, the round trip time. But equally, if the host isn't accessible, isn't on the local area network, for example, we will get back an error message from our ping saying that the host or the network is unreachable, as you can see in this example. So how do we get those messages is the next question. So how does ping work? What protocols does ping use? And how do we signal error messages across our network? So how do we find out if a host or a network or a protocol or a port is unreachable? What protocol is used to transfer that information? And you may have seen this one already, but it's IMCP, so the Internet Control Message Protocol. As always, there's an RFC for that, and you'll see that's 792. And you can tell from that number straight away, it's again one of the founding father protocols in our network. And that's because IP and ICMP go hand in hand. So it's designed alongside IP for this purpose. So like UDP, it's a very lightweight protocol. There's not an awful lot in that header there. Basically, you've got a type field and a code field. And your ever-present checksum, which will be used to checksum your header and your data. The data field does vary depending on the type of ICMP packet. We'll look at that in 2 ticks with the RFC. So a small subtlety, as you can see discussed here. So ICMP was designed in parallel with IP, so they go together hand in hand. So from one point of view, you could argue that ICMP is a layer 4 protocol because it uses IP as its transport protocol, the same as you would have with UDP and TCP. However, ICMP doesn't really carry user data. It's used to carry status or error messages associated with your IP transfer. So you could argue it's layer 4, but it's a little bit less than that. It's not a generic data transport protocol. So somewhere in the middle. You could argue it's layer 3 or maybe 3 and a bit. But anyway, getting back to our type field and our code field. So these are 8-bit values. So if we look at the type 1 first, here we have a table. So if your type code is the value 3, that is the type code indicating that something was unreachable. And then to differentiate between the different things that are unreachable, that would be your code value, as you can see here. So if you had a type value of 3 and a code of 3, then that would be port unreachable. If you had a type code of 3 and a code value of 1, that would be a host unreachable code. So the combination of the two there, you can identify what type of error state your system is in. So another common one is if you see a type code of 0, you know it's an echo reply from your ping command. And obviously there's only one type of reply packets, so you don't have any code fields. So that means if you see a type of 0, the code will always be 0 because it doesn't have to differentiate between the different types of reply. So as you can probably guess, in addition to our echo reply, we need an echo request that our ping command will be sending out, and that will be type 8, as you can see here. And again, because there's only one type of echo request, the code field is not used. If you want to look at the different types of ICMP packets, then the RFC is your best starting point, so 792. And if you look through that one, you will see that the structure of the packets does vary. So destination unreachable, that will be the format of this packet. So you've got type, code, checksum, we've got an unused 32, and then we've got a fragment of the original IP header that caused that error message. However, if you look at the packets sent by your ping command, the echo request or echo reply packets, you'll see they start off with the same format, but you also have type specific fields that follow that common header. So your echo request identifier and the sequence number. So that would be unique for each ping, and that will increment for every ping that you send. So they do vary a bit. And we can see that one in action. So you'll be doing this one in the lab, and we'll have a look at that one in the lecture review session. So we can just see a simple ping command happening here. So pi1 is pinging pi2, the -c is just for count for 4. So if we capture those ones using Wireshark, so here we can see our ping request coming out from pi1. So you can see it's been identified as a request, so type 8. We have our ping ID, so these identify as all coming from the same ping commands because they'll all be the same number. And here we have the sequence number that identify our ping count, replicating the number that is printed onto the screen. So here we have request 1 and reply 1, request 2, reply 2. You can also spot that you've got something strange going on here, so you can see sequence equals 1/256, and that's because of endiness issues. What is the most significant bit within those 8 bits? Is it little endian or big endian? So Wireshark displays both. And in the labs, we looked at some other ICMP packets. So we looked at our TTL field, for example. So remember, that is our def counter. So when that gets down to 0, when our router decrements that field within our IP header to 0, that packet is dropped. That router, if it's being nice, will send back a ICMP packet to the transmitting host. So a type 11 packet, telling that machine that its packet had got lost. At this point here, some people are probably shouting at the screen, Mike, why are you talking about ICMP packets? And this lecture is all about the data link layer. Obviously, ICMP are layer 3 protocols, whereas we're looking at layer 2. So the reason for this is I wanted to link back to those ARP packets. So when you do a ping, yes, you'll be sending ICMP packets, layer 3 packets between your hosts, but obviously your layer 3 protocol will have to discover the MAC addresses. And that's why when you do a ping, the first ping is typically a little bit longer than the subsequent pings, because in addition to sending your ICMP packets, you will also have to send those ARP packets to discover that destination MAC address. And so that was the whole point of that one. In addition to that, while I'm talking about this Wireshark screenshot, we can see the padding. So remember, we do have a minimum size for our Ethernet frames. So to pad it out to the required size, you do see, as you can see at the bottom here, the software will pad on some Crony finger time random characters. Obviously you can see here a certain sequence of characters to pad the packet up to the minimum size, which from memory is around about 46 bytes worth of payload, giving you a minimum frame size of around 64 bytes. Okay then, so we have seen that there are 4 main types of communication: unicast, anycast, broadcast and multicast. So we're going to pause and consider what is multicast. So we saw multicast in our classful definitions of IP addresses. So we saw that if the top 3 bits are set, then it's a class D network address. It is a multicast address. So it is a 1 to a set of receiving pool of hosts, rather than being 1 to all, which would be a broadcast. So fundamentally, you go, yeah, I can understand that one. I can see why we would need that one. But now if you start to put it into the context of layer 2, you go, how does that work? Because as we saw with our switches, if we are to do a unicast communication, then we'll be using our ARP protocol to work out which host I want to communicate to. So converting that IP address down into a MAC address. So what do we do with a multicast address? As we don't want to do a one-to-one communication, and we don't want to do a one-to-all communication, that would be the broadcast MAC address, all ones. We want to do a one to a select few communication. So how does your ARP protocol work with that? And as you probably guessed, we need a special MAC address for that. Okay, before we consider that, we need to consider how our multicast address, these 28 bits here, are split up, are allocated to specific functions. And as always, where would we find that information out? Well, the easiest place is to go to Wikipedia. So we can see here that our multicast address is split up into a number of different sections. And for this module, we'll be looking just at 2 particular ranges. So the first one and the last one. So the first one here are multicast addresses designed to operate on your local area network. So IP address 224.0.0.0 through to 224.0.0.245, and administratively controlled ones. So private multicast addresses. So IP addresses starting with 239.0.0.0 to 239.255.255.255. So fundamentally, multicast addresses that are not routable, that will be dropped by a router, and multicast addresses that are routable within your private network. So within the block of IP addresses allocated to your local area network, the first one that we will be looking at is the IP address 224.0.0.251. That is our multicast DNS address. And the key bit to remember here, when we look at the MAC address later, is ending 251 or FB. You'll see that later, so keep that in mind. So the easiest way to generate multicast packets on your local network is to do a multicast DNS lookup. So the intention here was to allow you to look up DNS type names on a local area network without the need for a DNS server. So if you had a fully qualified name ending with .local. Now, each host on the network is responsible for resolving its name. So a host on the network can do a multicast DNS lookup. It can put out onto the network a packet saying tell me the IP address for this name. Now each host on the network will resolve that query. So if a host detects that the query is for its host name, it will respond with its IP address. So no need for a separate DNS, it can all be done locally. And you'll see that, for example, with Apple's Bonjour protocol, which uses the same ideas. So for example, ping Raspberry Pi mail.local will be resolved using multicast DNS lookups. So if you were to issue that ping command, you will see going out on your network a multicast address of 224.0.0.251, or if it's IP version 6, FF02FB. Key finger spot is the port, so that will be going to port 5353, which in terms of DNS should look familiar. If it doesn't, do go back and look at that previous lecture where we looked at DNS. So for that previous ping example, you can see Pi1 has chucked out onto the network 2 multicast DNS requests or queries. So you can see you've got an IP version 6 and an IP version 4 destination address there. So a multicast destination address. So if you look inside our IP version 4 multicast packet, you can see we get our standard query as we would do with a dig command. So it's trying to resolve who's got this name and I want a IP version 4 address please. And as you can see here, our mail server does respond. Because it's listening out for that multicast address, it sees it's for him, so it sees it matches its name, so it'll respond with a reply, with an answer, and tell that machine its IP address. And you can see that is what is happening, because if you go back to our ping command, you can see it has resolved this name into this number. And this name here is not in the local hosts file. It's not in a /etc hosts. It is a name it has looked up using these multicast DNS lookups. But again, these will be limited to your local network. These will not be forwarded on by your router. So this works perfectly fine for our Raspberry Pi mail server, but can you see why it may be not so good to ping pi1.local? What issue would that cause? And as always, we'll chat about that one in the lecture review session. Okay then, so conceptually, we should be happy that we can see, okay, we're using a multicast address and I've got machines listening for that address in addition to their signed IP addresses for their particular NICs. But when we're working at layer 2, obviously we're dealing with MAC addresses. So what MAC addresses will be used in this communication? What will the destination MAC address be? And how we handle that one is with 2 multicast MAC addresses. So for IP version 4, you will see MAC addresses starting with 01005E. And for IP version 6, you'll see them starting with 333300. The lower 24-bit chunk is made out of the lower 23 bits of the IP address. So your multicast MAC address is based upon your multicast IP address, which is assigned to a particular protocol by IANA. Right then. So the previous example is a good example of local multicast. So multicast addresses that are confined to your local area network. But consider this scenario. So we want to stream a video to different computers within a building, and there may be multiple networks within that building. And we'll be doing that in the lab. The FTP server can also stream video, jellyfish videos, as you can see here. And it chucks those out onto the 239 network. And that is a routable multicast address. So that's all good. So if on your Raspberry Pis you start VLC or some other stream client, you can watch that video. So if you connect to UDP 239.123 port 4567, you will see that video stream. And the advantage of using multicast in this scenario is that you don't have multiple unicast connections to each host that wants to receive this video stream. Individual connections between the server and each client to stream this video. But obviously that will need a lot more processing power on the server side, and you'll be sending a lot more packets. Whereas if you're using multicast, you send the packets once. So the server sends out onto the network these video packets, and the clients that want to subscribe to this multicast stream will then access them. So it's a lot more efficient in terms of network bandwidth. But as you may have spotted already, that we have some issues. So consider this scenario. We have got the PC and it is perhaps streaming that video, and it goes to a switch. And we have our Raspberry Pis, and Pi 1 and Pi 3 want to watch this video stream, but Pi 2 doesn't. So how do we stop data going to Pi 2? Because the whole point of a multicast packet is that it's not a broadcast. You're not wasting Pi 2's time by sending it data packets that it doesn't want. So when the PC transmits this video stream onto the network, it will use the MAC address as we previously described. So it will use a MAC address 01005E123. And that MAC address will be sent to the switch. The switch obviously doesn't know where that should go. It hasn't got a record of that MAC address in its SAT table because this is a multicast destination address, not a source address. Remember, the SAT table is loaded with source MAC addresses, not destination MAC addresses. As always, if your switch receives a destination MAC address and that address is not in its SAT table, it will broadcast it. So effectively our multicast is turned into a broadcast, which defeats the whole point of a multicast packet. So what can we do about that? Well, as always, we need another protocol. We need IGMP, so the Internet Group Management Protocol. So IGMP is an integral part of IP multicast. And if you'd like some more information on this protocol, as always, there's an RFC for that, so RFC 2236. But basically it's a protocol that allows a client to join or leave a multicast group. And it does that again with a different multicast address. So in this Wireshark capture here, we can see a client with the IP address of 192.168.4.1 sending a join request onto the multicast address 224.0.0.22, which is the IGMP multicast address. So your switches and your routers can see that request, and if they support IGMP snooping, they can be more selective in where they send that data. So for example, if you set up your switch with IGMP snooping, if it sees a IGMP join request coming in on a port, it knows to forward that data from our multicast video streaming server to that port. So rather than broadcasting those packets to every port, it will only forward those packets to ports where it has seen a join request. So now we have our desired behavior. So if a client doesn't request to join this multicast group, then it will not receive these packets. As you've already spotted, there's some more complications. So the multicast address you can see here is obviously restricted to your local network. What if your multicast server is on a different network? How does the client then get access to this stream? So that's beyond the scope of this module. But fingers crossed, touch wood, we've introduced the basic ideas of what multicast is. Righto. So we have now finished looking at our network protocols. So we're at layer 2. We've looked at our lowest level protocols. And now we can back up that protocol stack to the application layer, perhaps to DNS, and see how those packets are transferred across the network through encapsulation, allowing them to be routed and received and processed by hosts on your network. But we still have some unanswered questions. We haven't looked at layer 1 at the moment. The physical layer, so our cables. How are the actual raw bit streams sent across our network? What cables do we use? What electrical signal standards do we use? Are all cables the same? And as you can probably guess, we'll be answering those questions in the next lecture. So I will see you then.